Okay, so way back at the beginning, we talked about showing a complete graph. A complete graph was all the x and y intercepts, all the max and min points, and no hidden behavior. Okay, this section is on predicting that hidden behavior. Okay, I'm going to go through some notes first, and then I'm actually going to take you through. You should be able to tell what your graph is going to look like before you ever graph it on a graphing calculator. Okay. First, let's look at a definition. Okay. We've talked about it in the other section: concave up, concave down. Now the author is going to define it. Okay. The graph of a differentiable function y equals f of x is concave up on the interval where the first derivative, where the y prime is increasing. It's going to look like this. The concave up is going to look like that. And if you think about your slopes of your tangent line, even if I said, okay, this is a negative slope, say that was like a -8 slope, then this might be like a -4 slope. It's still increasing. Okay, and then it's going to go to 0, and then it's a positive slope, like say a +2, +4, +8. It's increasing. Okay, so that's what concave up looks like. Okay, okay, and then concave down. And it's concave down on an interval where the first derivative, or y prime, is decreasing. So it's going to look like this. And if you look at tangent lines, okay, say this slope might be 8, and the slope of this tangent line might be 4, slope of this one might be 2. Okay, the slopes are decreasing. Okay, so that is concave down. Okay, concave up and concave down. Okay, now the test for concavity is the second derivative test for concavity. Okay, and it's concave down on any interval where y double prime, where the second derivative, y double prime, is less than 0. It's going to be concave down on any interval where y double prime is less than 0, and it's going to be concave up. And just ditto that on any interval where y double prime, or the second derivative, is positive. Okay. And I'll show you on a couple of examples how we test it. Okay, the next thing the author goes through is a point of inflection. I included a little bit of this in the first section, but in this section is where he actually covers it. The point of inflection, okay, is a point where graph, it's a point where the graph of a function has a tangent line and the concavity changes. So it's got to change from like concave up to concave down, or it's got to change from concave down to concave up. Okay, and we said it's going to look like this. You'll either have like this, and there'd be a point of inflection there. It switches here from concave down to concave up, or if we go this way, it's going to go from concave up to concave down. Okay. Okay, that's a point of inflection. Okay. If the first derivative, okay, is equal to 0, and the sign of f prime changes at C, then, okay, now think about this. If where is the first derivative equal to 0? Max or mins, okay? And if the sign changes at that point, okay, if before I finish this, if you have one like this, okay, the sign would change from positive slope, there's your max, to a negative. So if it changes from a positive to a negative, you're going to have a max. Okay. If it changes the other way, if it changes from a negative slope to a positive slope, then you're going to have a min. Okay. So if the derivative is equal to 0 and the sign of your derivative changes at C, then the function has a local extreme value at x equals C. Okay? And if f prime changes from a positive to a negative, that'd be like our first picture, then you've got a local max. And I know the book called it a relative max too. It's not an absolute, it would be a local. And then if the f prime changes from a negative to a positive, from a negative slope, that'd be like this one, from a negative to a positive, then you're going to have a local min. Okay. Okay, now with that, let's go through what they mean by a complete graph. Okay. And that's what it will say in the directions. Show a complete graph. On this, and we're going to try to do it by hand first, and then look at it on the calculator. The first thing you ought to do is find your first derivative, and then we're going to end up finding the second derivative. Okay? So you want to find first and second derivative. Okay, then you want to find values where the first derivative is positive, negative, and 0, and that's to confirm, where f is increasing, because they're going to ask you, where is this function increasing, decreasing? So it will confirm where f is increasing, decreasing, and where it has extreme values. And that's where it's equal to 0. So you do the first derivative, figure out where it's positive, negative, 0, and that'll tell you the intervals where it's increasing, decreasing, and extreme values. Okay? And then we're going to look at the second derivative. Find where f double prime, the second derivative, is same thing, positive, negative, and 0. And that's to confirm where f is concave up, and concave up is going to look like that. Okay, concave down, going to look like that. Okay, and points of inflection. So first derivative, you're going to find increasing, decreasing, and max and mins. Second derivative, you're going to find concave up, concave down, and points of inflection. Okay, and then the last thing, you're going to compare it with your calculator. And the author will call it your grapher or your calculator. Okay. Okay, now we're going to look at two examples by hand. Okay. And I want you to get a picture of what the graph looks like without actually looking at the graph. Okay. Okay. Okay, so first example. Say they ask you to graph y equals x cubed minus 3x squared plus 4. Now, you guys already have an idea of what a cubic graph looks like, okay? And it makes a difference whether this number in front is positive. Just like you should already know what a parabola looks like in x if the highest degree was an x squared. Okay, but first thing, they want you to find first derivative. Okay, so y prime, shortcut, use the power rule. What's the first derivative?
3x squared.
Yep, minus 6x, right? Okay, now set that equal to 0. Okay, and some of these you're going to be able to factor it. Okay, I always look at factoring first. If it's not factorable, then quadratic formula or complete the square. But this one is factorable. What's in common? 3x. So I can take a 3x out, and what's left would be x minus 2. Set both those equal to 0, so you'd have 0 equals 3x, divide by 3, and x would equal 0. Set x minus 2 equals 0, add 2 to both sides, you get x equals 2. Okay, okay, now, on your graph, okay, what I want you to do with the colored pencils is, okay, x equals 0. If I said graph x equals 0, remember that's going to be a vertical line. Okay, take a different color, okay, and then just graph x equals 0 would go right along the y-axis, okay? And then I want another one at x equals 2, okay? That actually separates your graph into sections. Everybody look up here for a minute. It separates your graph into negative infinity to 0, 0 to 2, and then 2 on. Okay? That's where the graph's going to be increasing, decreasing, max and mins. Okay? To find those, you also need the y value. Okay? So the next thing we're going to do is say, okay, x equals 0, x equals 2, Okay, now I'm okay with this. On your calculator, we're not going to look at the graph, but go ahead and put this in y sub 1. There's different ways to figure that y value. You can substitute in by hand, okay, and figure it out that way. So in y sub 1, we're going to put in x cubed minus 3x squared plus 4, okay? But we're still not going to look at the graph, okay? If I looked at the graph, I could do second function calculate, value at x equals. But instead, I don't want you to look at the graph, so go back to the home screen, do second function quit, okay, and now go to the vars key, V-A-R-S, the vars key. Right arrow over to y variables, okay, and then function, pick up y sub 1. It's just like if I said, if I wanted you to find f of 2, okay, I would substitute 2 into that, right? So we're doing the same thing. So let's find y sub 1, and let's do the 0 first. So if I put 0 in, that one you should be able to do by sight. With 0, 4. Okay, and then just do second function entry. Okay, and go back over and type in the 2. Okay, and the 2 should be 0. Okay, so basically we're just substituting in those two x values. Okay, now, so on your calculator it looks like this. Y sub 0 is 4, and y sub 1 of 2 is 0. Okay, that's what it looks like on the calculator. Okay, now we're going to mark those ordered pairs, 0, 4. So 0 to the right and up 4. Okay, so I'm right on the y-axis. Okay, and 2, 0, 0 to the right and up 2. Okay, so I have those two ordered pairs. Okay, now what I want you to do is to separate the graph, and now all I want you to do is to check from negative infinity to 0. Check any point out here back in the first derivative, and all I want to know is it positive, negative, or 0. So pick a point out here, like negative 1, negative 2. Put it into this, okay? Put it into this. Let's say I did negative 1. Negative 1 squared is 1 times 3 is 3 minus 6 times a negative 1. So I'd have 3 plus 6 is 9. It's positive. That means this is a positive slope. Okay? So far I'm starting to see my curve. Okay? Right now all I want is a line. Just a sketch. We'll come back and do the actual curve later. Okay, now you test a point in between 0 and 2. So an easy one to test is 1. When you test it, you're testing it back into the first derivative. And all I want to know is it positive slope, negative slope, or 0. So if you put 1 in here for x, 1 squared would be 1, times 3 would be 3, 3 minus 6 would be negative. So can you see the shape that we're starting to get for our cubic graph? And you can guess what this one's going to be. Test anything bigger than 2. Test like positive 3. 3 squared would be 9, times 3 would be 27, minus 18. Positive. Okay? So our actual graph's starting to look like this. Okay, but so far all I have is the lines. Just kind of a sketch. Okay? Okay. Now, you should be able to tell right there, where is this graph increasing, decreasing, points of max or min? Where is it increasing? Where does it have a positive slope? Okay, so increasing, where's the positive slope? From negative infinity to 0. And I will tell you the author's not real consistent on the numbers, whether he's using brackets or parentheses. I'm going to use brackets, okay? And then it's also, here's where it's increasing from negative infinity to 0. It's also increasing from 2 to positive infinity. And when we're talking positive infinity, we're talking positive infinity to the right, not positive infinity up, okay? Okay, where is this graph decreasing? Where does it have, when they say increasing, decreasing, all they're saying increasing is a positive slope. Decreasing is a negative slope. Where does it have a negative slope? 0 to 2. Okay? Now you should also be able to tell your relative max and mins, or local max and mins. So relative max would be at what, 0, 4? And the relative min would be at 2, 0. Okay? Everybody okay with that much? Okay, now you do the second derivative. Okay, so that means you got to take the derivative of the derivative. So y double prime. What would that be? 6x minus 6. You figure the derivative, you set it equal to 0. So 0 equals 6x minus 6. Factor out what's in common. Is a 6. And you'd have x minus 1. If we divide by 6 on both sides, it's gone, right? Divide by 6, so you'd have 0 equals x minus 1, add 1, x equals 1. Now pick a different colored pen or pencil. I'm going to use green. Okay, x equals 1. Okay, and separate your graph. Use another dashed line. Okay, then everybody look up here for a minute. That changes, okay, and separates your graph into two parts, from negative infinity to 1, and from 1 to infinity. Okay? Now, test a point on the left of 1. An easy one to test is 0. Put 0 back into your second derivative. If you put 0 back in here, negative. If it's negative, it means it's concave down. Okay, so, and that kind of is also already verified. From this point down, it's concave down, basically. Okay, and then if you test a point on the other side of 1, okay, let's test like 3. If you put 3 back in right here, you'd have 3 times 6 would be 18, minus 6 would be 12. It's positive. Positive means it is concave up. Okay? So, now you know we had a change in concavity from concave down to concave up, and the y double prime is equal to 0. Okay, so now we have a point of inflection. The point of inflection, the x value is 1. How do I find the y value? Go all the way back to the original. Now, I'm okay with you doing this on the calculator. Okay, if you go back in the vars key at the home screen, because we have it in the original. Okay, and if you sub in 1, you should get 2, right? My graph's a little bit off. That should be at 1, 2 for the ordered pair. So this is a point of inflection. Because it was where y double prime equals 0 and there was a change in concavity. Both of those have to be true. Okay, and we also did concave up, concave down. So we can do, for that, I'm just doing this. Concave down where? Where was it concave down? Negative infinity to 1. It always changes on the x values. Okay, and then where was it concave up? From positive 1 to positive infinity. You don't really have to say positive 1. It's okay to say 1. Okay. Now go back to your calculator. We've done everything. Graph it. Just do zoom 6. Okay, and it should compare with our graph. Okay, and then I would do probably a good graph would be in order. So you're going to have, yeah, we are good. Okay, So we had it changed. This was at 1, 2. My graph's a little bit off. 1, 2. It crossed. I'm going to have to be creative on my point selection here. And it went up to 0, 4, didn't it? 0, 4. Okay. That was a max. And then 2, 0. Ooh, it had to come down here, didn't it? Forget that part. Okay. My original graph's better than this. Okay. Okay. Get the idea? Okay, one more example. We're going to do this one together. See how far we get. Okay. Of course, the author's not going to make them nice, neat integers. Okay. Okay. Okay, so second example. F of x equals x cubed minus 2x squared minus 7x plus 2. Okay. First thing, find the first derivative. So f prime of x. Yep, 3x squared minus 4x minus 7. Okay. Set that equal to 0. It does happen that this one is factorable. If it's not factorable, then you go to the quadratic formula. This one is factorable. It's going to factor into 3x minus 7. You'd have to do a little bit. And x plus 1. Okay? Set both those equal to 0. 0 equals 3x minus 7. If you add 7 and divide by 3, x equals 7/3 or 2 1/3. Okay? Set x plus 1 equals 0. X equals a negative 1. Now, on your graph, okay, that's going to separate your graph. X equals 2 1/3. So, okay, pick a color at about 2 1/3. Okay, do a vertical line. At x equals negative 1, do another one. Now, you've just separated your graph into sections from negative infinity to negative 1, from negative 1 to 2 1/3 or 7/3, and then from 7/3 on. So that's where it's going to be increasing, decreasing. Then you have to find your max and mins. Okay. If you substitute back in to use your vars key, okay, you would. I'm going to go ahead and give this because we're running out. This would be 7/3 or 2 1/3, and it ends up to be negative 12.5. Okay, so 2 1/3 and negative 12.5. There's a point down here somewhere. Okay, and then at x equals negative 1, if you sub that back in, and remember you would basically put the original in y sub 1 and then go to the home screen and do the substitution. So at negative 1, 6, so there's a point up here somewhere at negative 1, 6. Okay, then you test. Okay, you have to test something to the left of negative 1. Pick a number like negative 3, okay? You sub that back into the original, put negative, or sorry, not the original. Sub that back into the first derivative, and all I want to know is that slope positive, negative, okay? If you put negative, let's do negative 2. If you put negative 2 back in here, negative 2 squared, 4 times 3, 12, that'd be what? 12 plus 8. 20 minus 7, so we got a positive. Okay, so we know our graph's doing this. Okay, and then an easy one to test between negative 1 and 2 1/3 would be 0. Put 0 back in, that drops out, negative 7. So it goes from there to there. Notice it connects the max and min points. And then if you tested like 3, it's going to be positive. So you can already tell what our graph's going to look like. Okay. Now, where is it increasing, decreasing? Where is it increasing? From negative infinity to to negative 1, union that with 7/3, yes, to positive infinity, yes. Okay, where is it decreasing? Oh, sorry, yep, negative 1 to 7/3. That's where it has a negative slope. Okay. Now you also can tell this point is a relative max, and this one is a relative min. Okay. Now you do the second derivative. So do f double prime. Go all the way back. Take the derivative of the derivative. So this would be what, 6x minus 4. Set that equal to 0. Okay, you can add 4 and divide by 6. Get 2/3 equals x. Right? Take another color. X equals 2/3. So right about at x equals 2/3. Do another vertical line. That separates the graph into two parts, from negative infinity to 2/3 and 2/3 to positive infinity. Okay? You need to find the y value. When you do the y value, put 2/3, and that's how I would put it in. I would put in 2 divided by 3 back in the original. Okay? And you're going to end up with a negative 3.259. So 2/3 and a negative, and that's about right. Okay? Okay, it's down here. Okay, then you check points to the left of that. An easy one to check is 0. You put 0 in here, you check it in the second derivative, you're going to end up with a negative. So that tells you this much of the graph is concave down. Okay, then you check something to the right of 2/3. Anything to the, don't check the max or min points. Check like 2 or something like that, and you'd end up with, put 2 in. 6 times 2 would be 12. So you end up with a positive. So this part would be concave up. Okay. Okay. So you know this then is a point of inflection. Okay, and then we can do concave up, concave down. So from negative infinity to 2/3, it's concave down. And from 2/3 to positive infinity, it's concave up. Okay, and then if you graph your original, okay, it should look like that. Okay. So, do first derivative, find the max and min points, separate your graph into x values. You'll find increasing, where it's increasing is where it has a positive slope, where your first derivative is greater than 0. Decreasing is a negative slope. Okay? And you'll be able to find your max and min. Then do the second derivative, set that equal to 0. Okay, that'll find your points of inflection. Find the y value for your point of inflection. Then there's got to be a change in concavity. Okay, so test points to the left and to the right back into the second derivative. If it's positive, it's concave up. If it's negative, it's concave down. Good? Okay.